Today, we tackle a fundamental geometry problem. Given a set of points, how do you determine if they all lie on a single straight line? It's a classic, but the brute force can be surprisingly inefficient. The problem, check if it is a straight line, provides an array of coordinates, where each coordinate is itself an array representing an x and y point. Our task is to return true if all these points form a straight line, and false otherwise. The core challenge is efficiently validating this collinearity for an arbitrary number of points. A naive approach would be to pick any three distinct points and check if they are collinear. If they are, we then pick another set of three, and so on. This involves three nested loops, one to pick the first point, one for the second, and one for the third. For each triplet, we use the cross product or slope formula to check collinearity. This leads to an O n cubed time complexity, as we're iterating through all combinations of 3 points. Space complexity would be big O of 1, constant time as we're not using extra data structures, but the time is far from optimal. The key insight for an optimal solution is that all points on a straight line share the same slope relative to any other point on that line. If we fix two initial points, say point 0 and point 1, we can calculate the slope between them. Then, for every subsequent point, we just need to verify that the slope between point 0 and this new point is identical to our initial slope. To avoid floating point arithmetic and division by 0, we can rephrase the slope equality y2 minus y1 divided by x2 minus x1 equals y3 minus y1 divided by x3 minus x1 as a cross product. y2 y1 multiplied by x3 x1 equals y3 y1 multiplied by x2 x1. This works even for vertical lines where x values are the same. We handle the base case of 2 or fewer points, which are always collinear, and then iterate from the third point onwards. Let's trace this with an example. Points 1, 2, 2, 3, 3, 4, 4, 5. First, we establish our reference points. Point 0 is 1, 2, point 1 is 2, 3. We calculate the change in x, which is 2 minus 1, so 1. The change in y is 3 minus 2, also 1. Now, for the third point, 3, for its x is 3, y is 4. We check if our original change in x, which is 1 multiplied by 4 to 2, equals our original change in y, which is 1 multiplied by 3 to 1. Both sides evaluate to 1 times 2, which is 2. They match. For the fourth point, 4, 5x is 4, y is 5. We check if 1 multiplied by 5 to 2 equals 1 multiplied by 4 to 1. Both sides are 1 times 3, which is 3. They also match. Since all checks pass, the points are collinear. After checking all points, since every new point maintained the same relative slope with our initial point 0 as point 1 did, we can confidently return true. All points indeed lie on a single straight line. You'll spot this pattern when dealing with geometric problems involving collinearity, or whenever you need to check if a property holds consistently across all elements relative to a base. The key is often to fix a reference and then iteratively compare against it, especially when avoiding floating point math is beneficial. The time complexity is big O of n, because we iterate through the points once after establishing our initial reference. The space complexity is big O of 1, constant time as we only store a few variables. Mastering these geometric properties can simplify complex problems. Try the next problem involving point transformations. Same pattern of reducing to simple math. Don't forget to like and subscribe for more DSA insights.